Hello everyone, welcome to lecture 2 of week 6 of the course Power Network Analysis, in which we will continue the discussion on the fifth main module of this course, which is transmission line models and the use of these models for understanding the performance of these transmission lines under different operating conditions. In this specific discussion or lecture, we will take up the discussion on medium line model representation for transmission lines. In the previous lecture, we had seen the discussion on the short line model, in which we understood that under different operating conditions, specifically for no load condition where the receiving end current is 0, for short line model, the Z parameters become undefined because it is as good as the short line doesn't exist under no load condition. The sending end voltage is same as the receiving end voltage, and the corresponding sending and receiving end currents on per phase basis, they are 0. It appears as if that the short line has been perfectly shorted at the sending and receiving end, and hence there is no role of any impedance at all, and that's the reason why Z parameters are undefined for short line model, not only for no load condition but for all operating conditions. Whereas in terms of other parameters for two-port network like Y parameters, ABCD parameters or H parameters, they are well defined for short line model under different operating conditions. That is one aspect. The other aspect is that we also talked about percentage voltage regulation for short line model. In fact, percentage voltage regulation is a very general concept, and it is not only applicable for transmission lines but for any other electrical equipment. In fact, for the upcoming models that we will discuss, medium line or long line, the same percentage voltage regulation notion would be true, which in a way is like if percentage voltage regulation of a line has to be evaluated, this is nothing but proportional to the receiving end voltage at no load condition, the magnitude, minus the receiving end voltage under full load condition with respect to some receiving end voltage under full load or no load condition. So that denominator is not so important, but what is important is that percentage voltage regulation is a measure of how much is the voltage drop or difference in voltage magnitude compared to line being loaded at no load till full load. And we saw for short line model that specifically under the case where the short line model is feeding in a leading power factor load, where the leading power factor load means that it is mostly a capacitive load capable of delivering reactive power. The percentage voltage regulation under such condition can become negative, which would mean that the receiving end voltage at full load or at full leading power factor load is more than the receiving end voltage under no load condition, which in a way is nothing but also known as Ferranti effect. We have still not seen about Ferranti effect. We will talk about it in the next few modules to come. I probably made a mistake in the previous lecture stating that short line model never ever encounters Ferranti effect. It was not entirely incorrect, but not fully correct also. The correct aspect which is the true for short line model is that short line model can also experience Ferranti effect, and it is probably due to the nature of load which is being served by the short line model. The short line model as such in itself doesn't have any capacitive modeling considered. So capacitance aspect is neglected or not considered in the short line model, especially the line capacitance is not considered. So there is no presence of charging current, and even if the line is energized, the line won't have any extra charging current being obtained from line capacitance, which is being neglected because line capacitance is absent. So my idea or intent was that Ferranti effect in short line model doesn't come up because of this line charging which is not being considered, but it can still happen depending on the type of load which is connected, specifically for leading power factor loads or capacitive loads. For lagging power factor loads, the percentage voltage regulation will still generally remains positive. So with that, now let's see what is our medium line model. So as we all understand by now that as the line length increases, the total line capacitance, although it is still smaller than the total line resistance and inductance, its effect probably cannot be still considered to be negligible. The quantum or the presence of line capacitance, total line capacitance becomes appreciable, and there comes a point or a line length or a voltage level where this capacitance is no more negligible. And as a result, as I was mentioning in the previous slide in context of short line model, the associated line charging current or capacitive current, which we discussed in the previous module while line capacitance was being discussed, its quantum becomes high, it becomes appreciable, which can also affect the nature of reactive power flow in the transmission line, specifically in the medium line model. So it can, as the transmission line gets affected through its reactive power flow pattern, the associated receiving end voltage generally can also be significantly different compared to the sending end voltage, which is the source voltage. And that's the reason why medium line model comes into picture, which is generally applicable for lines of length between 80 to 250 kilometers and operating voltage line to line being between 69 kV to 400 kV as indicated over here. We have also seen this in the previous lectures also, what the medium line model is. So basically the story is, or the concept or the nutshell is that line capacitance is not negligible for like medium line model, and those medium line models, they qualify under these conditions. So there's a difference of how line capacitance, if at all it has to be considered, because it is no more negligible. If it has to be considered, then its representation is going to be a little different, because generally line capacitance is treated as a shunt element, while line resistance and inductance appear as series elements in the short line model. So in medium line model, we will still have total resistance of the line, total inductance of the line, in which were also present in short line. And in addition to this, we'll also have the total line capacitance, which would be considered as part of the medium line model. And this capacitance cannot serve as a series element, so it has to be there as a shunt element in addition to the existing short line model parameters. And that gives rise to two typical models, two common models, I would say. One is called as the pi model, in which half of the line shunt, which is basically the line capacitance, half of it appears as a shunt element between the phase and the neutral or the ground on line ends, and that's what results in the pi model. The other model is T model, where the entire line capacitance as a shunt appears at the midpoint of the line, whereas on either halves of the line, half of series impedance, which is total resistance and the corresponding reactance due to inductance, appears in as half-half on either end of the shunt element, which is the line capacitance. So we will talk at length about these pi models and T models. Usually in the literature, the pi model is pretty common because it gives rise to certain convenience in terms of analysis, which we will see eventually in the next few lectures or next few slides to come in. The difference, however, is in terms of capacitance being considered, but the similarity between short line and a medium line model is that line parameters can still be assumed to be lumped, which are actually distributed, and as a result, the overall analysis with lumped representation and capacitance being considered doesn't lead to very significant differences in terms of actual analysis or actual perfect analysis, which eventually would come as part of the long line model, which we will discuss in the next lecture, and the overall assumptions that are involved in considering the medium line model. So the differences here in terms of accuracy is not very different, provided capacitance is considered in medium line model and parameters still remain as lumped and not distributed. So to start with our first model, the first common model for medium line, we call it as pi model. It looks something like this as shown over here in this figure, and we have the same notion of sending end, Vs and Is being the sending end voltage, receiving sending end current on per phase basis. On the receiving end, we have Vr, Ir, which are per phase receiving end current and receiving end voltage. And the neutral point here, or the reference here, is with respect to neutral or ground through which the potential is being measured, whereas the top wire is actually the per phase wire or per phase line of the transmission line. And as I mentioned earlier in the previous slide, pi model, half of line capacitance or shunt appears at either ends of the line, whereas the total line series impedance, which is R plus Jx, this X coming in because of line inductance, whereas these Y's are coming in because of line capacitance. So R plus Jx, the entire lumped representation appears at the midpoint of the line. And on a overview perspective, if we were to see how does this Z and R plus Jx they look like, they represent very similar to the pi symbol, which is the pi symbol present over here. And that's the reason why this model is also called as the nominal pi model. So I have hopefully given the explanation why it is called as pi model, because the architecture or structure or circuit looks like a pi model or a pi circuit in between sending and receiving end. Often the term nominal and not often, but nominal pi model is the most common terminology for defining these pi models, and often the term nominal is not very clearly explained in terms of regular textbooks. The reason why the term nominal comes in is because this nominal is indicating that this model what we are considering for medium line, it is still not an exact representation of the actual line. Actual line has still distributed parameters. The line capacitances are not present at line ends. They are still distributed. So in a way, the nominal word is referring to a notion that the model that we are considering is capturing only the essential features of the line. It is still not the exact representation. So to segregate out this feature, the term nominal is important in that context. And as I mentioned, the shunt admittance, which is the y by 2, y by 2 terms, which are coming in because of line capacitance, and possibly if conductance modeling were to be perfect, then half of line shunt admittance is capable of monitoring or sort of representing line capacitance and the conductance. So Z is equal to, as I mentioned, R plus Jx, where small r and small l are the per unit line resistance and inductance on a per meter or per kilometer basis. Omega is the source frequency, which is 2 pi f. F can be 50 hertz or 60 hertz. Capital L is the line length. And similarly, Y, which is the admittance, it is accounting for line conductance and line capacitance. G and C, small g and small c still representing per unit length line conductance and capacitance. Omega remains 2 pi f, and overall y can become capital G plus j omega c, where j, so there's a difference here. This is actually this is j omega c, not w, and j is the complex operator, which is square root of -1. So if conductance is not to be considered, then we would consider this factor small g to be 0, and in that context capital G would also be 0. Y would only be accounting for overall line capacitance. If we have to figure out certain mathematical equations which define this pi model, then basically we have two nodes. Let's say we talk about node S, which is sending end, and we talk about node R, which is the receiving end. At node S, by KCL, we observe that the incoming current is IS, and over here we have the outgoing current as IL. And since there is a capacitance present, assumed to be present, which is a lumped representation, along the source voltage Vs, there would also exist a current which is equal to Vs y by 2. So if we apply KCL, we have our first equation, which is sending end current is equal to the outgoing current, which is IL and plus Vs by 2. Similarly, on the receiving end, if we apply KCL, then we have IL as the input current to this node, IR is the receiving end output current, and across this shunt branch, again we have a current because of shunt admittance, which is VR y by 2. And that, so basically if we relate IL, IR and VR by y by 2 in terms of KCL, we get our second equation. Also, along S and R nodes, which are sending and receiving end nodes, we can apply or write KVL, and by KVL we would get Vs is equal to VR plus IL into Z. So that's what this relationship is again mentioned here. So this is our third defining equation. We have all our equations in place. Vs, Vr, Is, Ir, Il, they are all per phase quantities for a per phase equivalent representation. And as I mentioned earlier, the reference point or potential measurement point is being measured with respect to neutral or ground. So we can always rewrite these equations in terms of well-known parameters for two-port networks. For transmission lines, generally ABCD parameters are common. So if we rewrite or rearrange them, so what is done here is we have replaced IL in terms of IR and y by 2 VR. So we get our first ABCD equation where, remember, in terms of ABCD parameters, Vs is equal to AVR plus BIR, and the second ABCD parameter equation is Is equal to CVR plus DIR. So what we are trying to do is we are trying to re-represent these three equations in terms of these ABCD parameter equations so that we can get to know our ABCD parameters. So essentially, if you make a one-to-one correlationship here, then basically this term is nothing but capital A and this term is nothing but capital B. Similarly, if we substitute IL is equal to IR plus VR by 2 in the first expression over here and present Vs also again in terms of VR and IR in this term, we would get Is as this larger term, which again when simplified results in our second equation of ABCD parameters. So essentially, if we compare this equation with the equation given over here, we have C as this term, whereas we have D as this term. And that's how the ABCD parameters can be evaluated. Coincidentally, A and D, they are equal to 1 plus zy by 2, whereas B and C, they are unique numbers. And as per condition of symmetricity, A should be equal to D. Pardon me, there's a mistake here. It is not equal to 1. There's a mistake here. It is only A equal to D, which is equal to 1 plus zy by 2. Which is obvious from the medium line pi model. And if we evaluate AD minus BC, so let's do that. A is 1 plus zy by 2, which is also equal to D. So basically we have square here, minus B is equal to Z into C is Y 1 plus zy by 4. So if we expand the first term, we have 1 plus z square y square by 4 plus zy. Then we have minus zy, opening up the bracket inside the term. Again minus z square y square by 4. So our terms, they get cancelled and essentially we are only left with 1, which is essentially what is also mentioned, or which is also the condition for the condition of reciprocity. So basically our nominal pi model for medium line also is a linear, time invariant, passive, symmetric, reciprocal network. That is essentially what I am trying to explain here. Please note that the ABCD constants that we are evaluating, because Z and Y, they themselves are complex numbers. Remember, Z is equal to capital R plus JX, where Y is capital G plus J omega C. Z and Y themselves are complex numbers, and A, B, C, D, they are functions of Z and Y. So it's obvious that ABCD parameters would be complex numbers and they represent appropriate sensitivities. Now, what are these sensitivities? These sensitivities are, so essentially if I write the equation of ABCD here, Vs, Vr plus BIR and Is is equal to CVR plus DIR. So under the condition when the receiving end current is receiving end current is 0, means the line is at no load. The value of A is equal to Vs by Vr, which is as per the definition of A under the condition that IR is equal to 0. And similarly, the value of C is equal to Is by Vr, again on the condition of IR being equal to 0. So C and A, if we see, they're essentially sensitivities between the sending end voltage and current with respect to the receiving end voltage, and that's the reason or notion of defining sensitivities. Similar notion is also true for constants B and D when the receiving end part of the medium line model is shorted, where VR becomes 0. And just to highlight that ABCD constants which we evaluated for short line, they also are in general complex numbers, because in short line, capital Z, the series line impedance is still function of line resistance and line inductance. So in terms of re-representing the receiving end quantities in terms of sending end quantities, we can take the inverse of ABCD matrix, And coincidentally, this ABCD matrix does have a inverse because it is representing a condition of reciprocity. Basically, AD minus BC also happens to be the determinant of this ABCD matrix here. So if AD minus BC is equal to 1, as long as the AD minus BC term is not equal to 0, ABCD matrix is factorizable, and if we do that, we get this as our inverse term. So from there, we can also try to find the receiving end quantities as functions of sending end quantities. So if we know the sending end quantities, we can put them in this equation and get our receiving end quantities. Once we know ABCD parameters, we can also make use of those ABCD parameters and convert this model into relevant Z parameters based two-port network, Y parameter or H parameter based network. So in terms of Z parameters, this is the basic equation for defining the Z parameter based two-port network, which in terms of A, B, C, D can be defined or obtained as per these conditions. Please refer to our previous slide or previous lecture discussion where these interchanges or exchanges were defined. Similarly, for Y parameters, the conditions of symmetricity and reciprocity are again defined, and in terms of ABCD, we can again find these numbers for Y parameters. Same is also true for H parameters. As long as we understand what is H parameter representation, we can correlate or re-represent our ABCD parameters in terms of H parameters, which are what are shown over here, where still the conditions of reciprocity and symmetricity are still being valid. So moving on to our nominal T model, we have talked about the nominal pi model. In terms of nominal T model, the term nominal still refers to the fact that the model that we are considering is not an exact representation, but it is only capturing the essential features of the transmission line. And in T model, as I mentioned, the entire line capacitance is present at, or the entire line shunt is present at the midpoint of the line, where half of the series impedance Z is present on either half of the lines, where Z, capital Z is again R plus JX, which is what we have defined over here. This W is actually omega, which is equal to 2 pi f, not the small w. And if we try to understand the mathematical equations which define this model, then at the midpoint of the line, we apply KCL. So let's say if we take this node, then the input current is IS, output current is IR. We are assuming a fictitious voltage V, so the current across this shunt element is V into Y. We apply KCL, we get this equation, and then we also have three nodes which we can talk about. One is sending end, receiving end and the midpoint. So if I apply KVL across sending end and the midpoint of the voltage, we get Vs is equal to V plus Is Z by 2. And for KVL across node V to receiving end R, we have V is equal to VR plus IR Z by 2. So again, we have three equations, similar to the three equations which we got for nominal pi model. Using these equations, we can again rewrite them. So one straightforward way is we substitute V from VR and IR over here. We would get our second ABCD equation, which is 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 equal to CVR plus DIR. So if we combine these two equations, we can get C and D parameters for nominal T model. And likewise, if we substitute V over here and Is from here, we can get our first equations. If we do that term by term correlation, our ABCD parameters, again, they can be defined in this term. Again, there's a mistake here. It is not equal to 1. It is actually A is equal to D is equal to 1 plus ZY by 2. Where condition of symmetricity is still true, and B and C terms, they are exchanging their values in terms of nominal pi model. So the roles of B and C, they have now changed. Earlier, for nominal pi model, B was simply equal to Z, whereas C was equal to Y into 1 plus ZY by 2. Sorry, Z into 1 plus ZY by 4. Now here the values of B and C, they are interchanging with respect to nominal pi model compared to the nominal T model. And again, AD minus BC is equal to 1, which indicates that the condition of reciprocity is still true. Similar to representing Z parameters, Y parameters and H parameters, for nominal T model, again we can use the same interchange relationships between different two-port network parameters and obtain other values in terms of Z, Y and H parameters. So with that, let's understand which one of these models, whether the nominal T model or the pi model, is convenient. Usually the nominal pi model is very convenient for the upcoming discussion, specifically for power flow or for fault analysis, due to easy calculations and easy interpretation of the network. And even if we were to argue that, oh, let's choose nominal T model or nominal pi model, the differences in terms of actual analysis will be marginally different, not very different. So from operators perspective, from network owners perspective, from engineering perspective, nominal pi model is generally considered. And once we do all our analysis, we can again get back to our complex analysis equations, where we can find out the corresponding per phase sending and complex power, receiving and complex power. The choice of using whether the pi model is to be used or T model is to be used depends on what is the operating voltage, line length, whether what trade-off are we looking at in terms of accuracy. So I'll conclude this today's discussion, with two examples. The first example, we have a medium line model, or a medium line which is of 130 kilometer long. The values of small r, small l, small c on per kilometer basis are defined. The receiving end load is a lagging load of 270 MVA with 0.8 power factor. The receiving end voltage is mentioned at 325 kV line to line, and we have to find the corresponding sending end quantities and the voltage regulation using the nominal pi medium line model. So the first objective is to find what are our capital Z and what is the capital Y. Z is the series impedance, which is the value over here. Capital Y is the effective line capacitance, which is also evaluated in terms of omega inverse. And we have understood what are the nominal pi model ABCD parameters, so we can plug in those values of Z and Y as per the requirement and get all these numbers in terms of ABCD parameters. Once we know the ABCD parameters, it's now time to find what are the receiving end quantities. We are choosing receiving end voltage as the reference for all phasors. So from there we can find the corresponding receiving end current. So IR is the mod or magnitude of IR, since the power factor is 0.8 lagging. So receiving end current is lagging the receiving end voltage by 36.87 degrees. Receiving end power, 3 phase, is 270 MVA. So per phase power is 90 MVA. From the 90 MVA fact, we can find the corresponding current, which is this per phase current here. And once we know what are our VR, IR, we also know what are ABCD parameters. So we can plug in those numbers to get our corresponding sending end voltage, which is this number. We can also find our 3-phase line-to-line voltage and the corresponding sending end current and sending end complex power. In terms of power factor, if we were to see, the receiving end load is actually having a power factor of 0.8 lagging, and if we try to observe the power factor at the sending end, it is not exactly same as 0.8. It is different from 0.8. In fact, it is better than the receiving end power factor. It's tending to be closer to 1. And the reason for this power factor improvement is the line capacitance is now coming into picture. So majority of reactive power is not being fed from the sending end. The line capacitance itself is capable of feeding in this lagging power factor load. So sending end power factor is improving. There is a lesser requirement of reactive power from the load perspective, which is to be fed from sending end source. The line can take care of the reactive power hunger or need for the load, and that's what is leading to improvement in power factor at the sending end. In terms of voltage regulation, the usual expressions can be used, and we see the voltage regulation is close to 6.155%. The same example, if we were to solve using nominal T model, the values of Z and Y, capital Z and Y, they remain the same. The ABCD parameters, they might be different. Specifically, B and C parameters are different. And we do a similar exercise. We find the receiving end voltage. We choose that as a phasor. We find receiving end current. The quantums or the values still here, they remain the same. Now with new ABCD parameters, if we now find Vs, the value is little different. Earlier it was equal to 199.1889 volt, and the sending end apparent power was 345 kV. 345, sorry, there's a difference. 345 kV was the line to line voltage. The sending end power was somewhere around 218.124 MVA. The same number, if we see here, the differences are not very different. Here, the earlier we had 345 kV as the value. The sending end voltages, they are still more or less same. The sending end currents, they might have they have changed. So, and the power factor also has improved because the differences have now gone up in terms of nominal T model. The voltage regulation is also more or less similar. Earlier it was 6.155%. The differences or the notions here in terms of red colors, they are not very different from nominal pi model. That's the bottom line story. So in the next lecture, we will start with our discussion on long line model, where we will understand how actual transmission lines can be modeled and see comparison between short line, medium line and long line model in the upcoming discussions. Thank you.